Today we're going to be going over logarithms, part one. Let's say we had an equation and it said f of x is equal to 2 to the x, and we graphed this on the following graph. Well, what if I asked you what happens when 2 to the x is equal to 20? What could that value be? Well, we know that whenever we have 2 to the x, we can actually count using exponents, and we can say 2 to the first is equal to 2. We can say 2 to the second is equal to 4. We can say 2 to the third is equal to 8. We can say 2 to the fourth is equal to 16. And we can say 2 to the fifth is equal to 32. So we know 2 to the x, when it's equal to 20, has to be somewhere in between 2 to the fourth and 2 to the fifth. So it's going to be a decimal, but we don't know exactly where that value is. If I got this graph and I said, okay, let's see where it would land. Well, here is when our y is 20, or f of x, because remember, f of x is the same thing as our y. Well, whenever it's equal to 20, we can look across to our graph and we can say, well, 2 to the x is equal to 20 right at that point right there. And if I were to go straight down, I can tell that my 2 to the x is between my 4 and my 5. So I know my x for my exponent has to be between 4 and 5, but I don't know the exact value. Well, there's a method that we can actually use so we can get a very, very close answer. So we don't have to estimate that it's somewhere between 2 to the fourth and 2 to the fifth. We can actually get something more exact. So what we're going to be looking at today is we're going to be looking at inverse operations. We know the opposite of addition is subtraction. Because I have 3 plus 2 is equal to 5. Well, I could also rewrite this and say 3 is equal to 5 minus 2, because addition and subtraction are inverse operations. If I were to look at multiplication, I know the inverse operation of multiplication is division. 5 times 6 is equal to 30, but I also know that 5 is equal to 30 divided by 6. So these are related. If I were to look at inverse operations using something that's squared, I can say, okay, well, 7 squared is equal to 49. Well, I can also say that the inverse operation of squaring something is to take the square root. So if I wanted to, I could say the square root of 49 is actually equal to 7. This goes along with cubing as well. If I wanted to take the cube of something, I know the inverse operation, or how to undo a cube, would be to take the cube root. So 5 to the third is equal to 125. I could say the cubed root of 125 is equal to 5, because I know 5 times 5 times 5 is 125. Well, the inverse operations of exponents are actually called logarithms. I could actually rewrite this and I could say the log base 2 of 32 is equal to 5. Now, logarithms aren't something that you're used to seeing. So what we're going to do is we're going to talk about logarithms, and I'm going to show you how we can rewrite them, because logarithms, what they really do is they tell you how to figure out exponents. So we're going to look at the definition of a logarithm. If b to the x is equal to a, then we can actually rewrite this so that way we can figure out what our exponent is. And one of the things that I like to show you is that we can actually circle what order we're gonna put our stuff in. So I'm gonna do a weird looking circle around my b and my a. Kind of looks like a bean, okay? I had some of my students say it was called the whale. You can call it whatever you want, but do a weird looking circle where you circle your base and you circle your answer. So we have log And the first thing we circled was our base. So our base becomes our base on our logarithm. So this is still the base, but now it's the base on the logarithm. And then the a, or what it's equal to, the answer, that is actually called the argument. And it's always going to equal the item that you did not circle, which ends up being our x, or our exponent. So this just tells you how to rewrite our problem so that way we can actually figure out what our exponent is. So we're going to practice rewriting this. Let's take a look at going from exponential form to logarithmic form. Well, if I have b to the x is equal to a, I'm going to do that weird looking circle where I circle my base and my answer, and I'm going to rewrite it as a logarithm. So I'm going to write the word log, short for logarithm. Then the first thing I circle is my base. The second thing that I circle, my answer, becomes my argument, and it's always going to equal the exponent every single time. Let's do it again. If I wanted to go from my logarithmic form to my exponential form, I'm going to do the same thing. I'm going to circle my base and my answer. And whenever I rewrite it, my base becomes the base of my exponential equation. My answer becomes my exponent, and it's always equal to the argument, or the thing that we did not circle. So we've gone from the logarithmic form to the exponential form. We're going to rewrite the following into the designated forms. So if I look at this one, it says on example 1, we're going to go from exponential form to logarithmic form. So remember, you circle your base and your answer. And when we rewrite it, we're going to say it is log. The first thing you circled becomes the base of the logarithm. Your answer becomes your argument. And it's always equal to your exponent, or the part that you did not circle. Let's take a look at example 2. I'm going from exponential form to logarithmic form. So you circle your base and your answer. And when we rewrite it in our logarithmic form, we're going to write our log. The first thing we circled becomes the base of the logarithm. The second thing we circled becomes the argument of the logarithm, and it's always equal to that exponent. Example 3, same thing. I circle the base and the answer. And even though this is a fraction and it looks a little weird, we're going to write it the same way. We're going to write the log of the first thing that we circled was the base. So it becomes the base of our logarithm. And then our answer becomes the argument. So we have 1 over 36. Close my parentheses, is equal to, and then that -2. Now, one of the things I do want you to notice is that my base on my exponential form, when it becomes a base on our logarithmic form, it's always a little smaller, a little lower. Okay, it's not the same size as the rest of our stuff. It's a subscript, you can say. If I wanted to go from my exponential form to my logarithmic form, same thing. I'm going to circle my base and I'm going to circle my answer. I rewrite it using log. The first thing I circled becomes the base of my logarithm, and then my answer becomes my argument, and it's always equal to that exponent. Let's take a look at example 5. Same thing. I circle the base and the answer. I rewrite it so it's the log. The first thing I circled becomes the base of my logarithm. The second thing I circled becomes my argument, and it's always equal to that exponent every single time. Same thing for the next one. I circle my base and my answer. It becomes log. The first thing I circled was my base, so it becomes the base of my logarithm. And then the second thing I circled becomes my argument, and it's equal to my answer. Now you notice that sometimes I write the parentheses on the logarithm, or logarithms argument, and sometimes I leave it off. It doesn't matter if you leave it off or put it on. The only time it does matter is if you actually have a polynomial in there, you would have to put it in parentheses if you are taking the log of the entire polynomial. Let's take a look at the next one. Let's say I wanted to rewrite this one. Same thing. I circle my base and my answer. and I rewrite it so it's the log. The first thing I circled becomes the base. The second thing I circled becomes the argument, and it's always equal to that exponent every single time. And this just gets us comfortable rewriting our logarithmic forms and our exponential forms. Now we're going to do it the opposite way. We're going to go from our logarithmic form to our exponential form. So I'm going to circle my base and my answer. And now whenever I rewrite this in its exponential form, I'm going to rewrite this so my base is now the base of my exponential form. The answer turns into my exponent, and it's equal to that argument, or what I didn't circle. And notice the log just goes away because we're rewriting it in its exponential form. If I look at example 9, I have my logarithmic form to my exponential form. I'm going to circle my base and my answer. And whenever I rewrite it, I'm going to write my base to my exponent is equal to that argument. On example 10, same thing. I'm going to circle my base and my answer. Whenever I rewrite it, it becomes the base of my exponential form to my exponent is equal to, and then that argument. Thanks for watching. Now you know how to rewrite exponential forms into logarithmic forms, and you know how to write the logarithmic forms into its exponential forms.